Hi guys, today we are going to be doing a one sample proportion significance test. And so to begin this problem, when you're doing a significance test, and this is our very first one, it's going to be very similar to confidence intervals, but there will be slight differences, so you want to pay attention to what those differences are. So the problem that we're going to look at today is that an airline who loses passengers' luggage, well, I guess that's every airline, they claim that when it's lost, they will recover 90% within the first 24 hours. So what a consumer group did is they surveyed a large number of air travelers, and they found that their proportion was 103 out of 122. So they found a proportion that was quite a bit smaller. It was actually 84% versus the 90% claim. So what we're trying to do is we're trying to see, is this a large enough difference where we would doubt what the airline is claiming, because we know that it's not always going to be exactly 90%. Sometimes it'll be over, sometimes it'll be under. The problem is when it's very far away, that's something that we would call statistically significant. It doesn't just happen by chance, it's something weird is going on or the claim was wrong to begin with. So when you start to do a significance test, you're going to have your HO and your HA. So HO, write that over here, and your HA. That's the null and the alternative hypothesis. And the null hypothesis, so you have to make a decision. Is this a mean or a proportion problem? This would be a proportion because I am, you do see how it's like 103 out of 122? 90 is a percent. So that's how I know I'm on a proportion problem. It doesn't say anything about averages or means or standard deviation. So I'm going to use the Greek letter pi is equal to 0.90. That's the claim. That's all you have to go off of. The alternative hypothesis, though, is that we think it's not quite 90%. We think it's 0.84. No, that's wrong. We think it's less than 90%. And that's kind of actually my first mistake here is you always use the same numbers. So if 90 goes there, 90 goes there, you start with equals, and then this will be less than 90%. So one of the things that you have to define is your Greek letter. You have to define that. So I would say where pi is the proportion of lost luggage recovered within 24 hours. That's the true population. Actually, let's do that. Pi is the population proportion of lost luggage recovered within 24 hours. So if I'm using a Greek letter, I'm going to be using, it's going to be going to be the population. Okay, so now the other variables that come into play where you don't have to actually define these, but we've got our p hat, which is 103 out of 122, and that's 0.84. And we also have our n, which is 122, and that's 122 people with lost luggage. Okay, now you do not have to write in words what n is. You don't have to write in words what p hat is. You do have to do the Greek letter. Bare minimum, you better make sure you're doing the Greek letter. I'm going to do the sample proportion. I'm going to do it just to help me and help you just kind of get into the routine of doing things. So 0.84 is the sample proportion of lost luggage recovered, and I'd say within 24 hours. So I just use the dittos. So it's kind of just saying what the pi was, but this is the sample proportion. So now I have to add one other thing, and this is alpha. This is 0.05. This is what we call your significance level. If they don't specify a significance level, you're going to use 0.05. Sometimes they do specify. This is going to be the cutoff for something that is rare or something that is not so rare. And that's, you only need it when you're talking about a significance test. So, HO, HA, define your Greek letter, which is right here. Okay, so that's the first part. And then that we usually is kind of doing this is going to be one step in a significance test. The next thing you're going to do is your conditions. So you're going to title it, and your conditions for a 1 sample proportion, and I'll just call this a z-test. Proportions are always z's, by the way, never t-tests. Okay, so number 1, and hopefully something you're somewhat familiar with is, it's going to be very similar to what you've already done. Is it a simple random sample from the population of, people who've lost their luggage? So is it a simple random sample from the population of people with lost luggage? Okay, and then I look back in the problem and, and we kind of see, did they take a random sample? And it says they actually just surveyed a large number of air travelers. So here would be a situation where I would write something along the lines of like, no, but seems to be representative a simple random sample. Okay, we have no reason to believe that their sample does not represent what a simple random sample would look like. So I know it's weird and these things are not always cut and dry, but sometimes you'll just have to assume it to proceed. But in this case I'd say no, but it seems this sample does seem to represent. Number 2, because we are sampling without replacement, we have to check, is the population greater than 10 times n? So, and this is something that's going to come up, whenever you are sampling. So, they did take a large number of air travelers. They're sampling from the entire population of air travelers. So this would be, and I'm not going to make you write, sampling without replacement, but we're going to write, is the population of lost luggage air travelers greater than 10 times n. So is it greater than 10 times our sample size, which is 122, which is 1,220. And in this situation, I would say yes. I'm sure there are way more than 1,220 people who lost their luggage, when traveling. So, we can say yes. You can also say it's assumed to this. So what happens is these two conditions are going to come together and show you that you have independent lost luggage travelers. So we're going to write, therefore, independent lost luggage travelers. Okay, or something along the lines of like independent people who've lost their luggage. We know that these people are independent. Okay, so now number 3 And number 3 is always the thinker, whether you're on a mean or a proportion. Now, if we were on a confidence interval, which is what you guys have just gotten done with, you would be doing n times p hat if it's a proportion, and n times 1 minus p hat has to be greater than or equal to 10. But in a significance test, you actually have something better that you can use. If you have the Greek letter, we do. Shows up in HO and HA. It does not show up in a confidence interval. If you have the Greek letter, use it. So instead of np hat, we're going to use n times pi and n times 1 minus pi. Okay, so we're going to show those. So we got 122 times 0.90, that's pi, Greek letter, and 122 times 1 minus 0.90. And we're getting 109.8 and 12.2. Pretty darn close, but both of these are greater than or equal to 10. So what that means is that, therefore, we can say that a normal approximation is okay. And that's important because that is what allows you to proceed to draw your normal curve. Now, if you have the Greek letter, that's what goes in the middle. And we do have the Greek letter from HOHA. This is 0.90. This is the claim. The claim goes in the middle. The sample goes on the curve. So we're going to put 0.84 on this curve, and we are going to shade to the left because we're trying to see if it casts doubt on the claim, which would mean less than 90% is recovered. Now, back in the old days, guys, when you had to find this area, you used your good old Z formula. I'm going to write it really small, and don't, you just kind of off to the side so you can see the generic form. Z is equal to X minus Greek letter divided by sigma. Okay, don't write this, but just use this as a guideline, okay? Now, so this is sample minus statistic divided by the standard deviation of your sample statistic. So what I want to do is show you the generic form of this. It's at the top of page 5. You'll be using this for confidence intervals, which you've already done. You see the standardized test statistic, and notice how it says statistic minus parameter divided by the standard deviation of the statistic. And also notice the standard deviation of the statistic is actually right here. Standard deviation of the statistic. If I'm on a proportion, I'm going to use this. Please remember that P is pi. P is the Greek letter pi. P hat is the sample. Okay, so for a sample proportion, I'm going to take the statistic, which is I got to write the formula. So Z is equal to P hat statistic minus the Greek letter parameter, pi, divided by the standard deviation of the statistic. Standard deviation of the statistic, come right here. You're doing a proportion problem. This is the formula we want to use. P is pi. So we're going to do the square root of pi times 1 minus pi divided by n. And that is equal to, so formula, substitution. Okay. Now, back in the day, when you were trying to find this area, you would find a Z value. And then you would go into your calculator, normal ZDF, and you do negative 999, comma, whatever this Z-score is, right? Now what's nice is we have calculator buttons very similar to the ones that you use for confidence intervals. So I'm going to have the calculator calculate that. So where do we go? Clear. Okay, stat, test. And we are doing a one-prop z-test. If you are doing a proportion, make sure the calculator has prop in the title. If you go over here to a z-test, right here, number 1, it does not have proportion. That's for means. You're going to do a one-prop z-test. Okay? Press enter. Number 5. P-naught, that's your pi. That's the null hypothesis, which is 0.9. Now p-hat, please listen to this carefully. They don't want the 0.84. They want the fraction that was used to create the 0.84. So if you look all the way up here, p-hat is 0.84. But I want the fraction 103 out of 122. That's what you're going to put in the calculator, 103, 122. And now I'm going to do they say it's a less than, right? Alternative is less than. So just take this sign that's less than, that's in the alternative, and just match it up with that. Don't do too much thinking. If that's a less than sign, you highlight a less than right there. So I do that. I hit calculate, and it's going to give you a bunch of stuff that you used to have to do individually. So it's going to give you the z value, which is negative 2.05. So copy that down. Z is equal to negative 2.05. I'm going to put that right there. Okay. Now the other value that I care about, okay, look over here. Okay, notice p-hat is 0.84, your n is 122. It's this guy right here. That's called the p-value. The p-value, it's not pi in this situation. It's actually called the p-value that they're giving you. P is equal to negative, you can't have a negative probability, 0.02. So we'll write that. So p is equal to p-value equals 0.02. Now this is where you're going to make your decision. I have special ways to do this. So let's just do it, and then I'll explain how this works, okay? So we are going to write, since the p-value is less than alpha equals 0.05, we reject HO. Okay. If your p-value is smaller than 0.05, you reject HO. Okay, so we're rejecting the company's claim. The second sentence is going to talk about your the alternative hypothesis. So you're basically going to say that in words. If we reject HO, there is sufficient evidence to conclude. And basically, I'm either going to look back at the last sentence, there's doubt on the airline's claim, or I would just say what the alternative hypothesis in words, which would be the proportion the population proportion of luggage recovered is less than 90%. Okay? The first sentence talks about the null hypothesis. Are you rejecting or failing to reject? The second sentence talks about what the alternative is saying. Okay, so I have two ways to remember this. I call it PLAR and PGAFFR, and I've actually added on to those. So let me turn this over and explain to you what those are. Okay, so I've added on, it used to be PLAR and PGAFFR. I'll write this down here. Okay, but I've actually added on to it. It's actually become PLAR-TIS and PGAFFR-TINS. So it sounds like, I don't know, that sounds like something from The Hobbit. But PLAR-TIS is a disease, and PGAFFR-TINS sounds like, yeah, Hobbit. Okay, so PLAR-TIS. If you can remember these acronyms should be there to help you remember whether you're rejecting or fail to reject. So if P value is less than alpha, so P less than alpha, so P value less than alpha, reject HO. Reject. There's the PLAR. Now the TIS says there is